Hello, I'm Matt Perks and I'm the lead tutor for the PGCE secondary science programmes at the University of Southampton. This session is an introduction to some ideas about how children learn that may be useful to teachers. May be useful, that sounds a bit unconvincing. As teachers, learning is what we want to make happen in our lessons, and learning is one of the things psychologists study. Surely psychologists must have a lot of useful things to say to teachers about how children learn and how to make teaching and learning more effective. There are several problems though. Psychology is a young science. Quite a few important discoveries in psychology are proving hard to replicate at the moment, for example. Even the best lab research doesn't necessarily translate to the classroom. Although you can look inside of the brain, or sort of look inside the brain with functional magnetic resonance imaging, it doesn't tell you very much at the moment, and the whole thing is just very complex. This diagram shows one way of dividing research psychology into fields. How does classroom learning fit into this? Well, there are probably bits of everything that contribute. In this session, we are going to look at some ideas from cognitive psychology that seem useful. Then we're going to look at some ideas from developmental psychology that have heavily influenced teaching but have some problems. Finally, we're going to look at another idea that's well known but wrong. I have to say that if you have a notion that psychology might give you some kind of recipe for effective teaching and learning, then I'm afraid you're going to be disappointed. But there are some useful ideas. Let's have a look. This diagram shows the most widely accepted model for the way memory works as we handle and process information. It's called the Baddeley and Hitch model. It's based on careful experimentation on memory with replicable results. There are some different versions, but the key point is that our capacity for paying attention to something, to holding it in mind, is really very limited. So look at the diagram. At the top is stuff coming in from our senses. In the middle is working memory. So there are 3 rectangles there. That represents working memory. And that's the bit where we're paying attention to something. That's the important bit from this model, and I'll come back to it in a moment. Then at the bottom is our long-term memory. As far as we can tell, our long-term memory has unlimited capacity, but we can struggle to retrieve ideas from long-term memory depending on how often we use those ideas and how much they are tied to other ideas. We'll look at how we get ideas into long-term memory and improve retrieval of them a bit later. Now, what about that very limited working memory, the middle section of this, the middle row, if you like, of this model? The central executive represents what we're actually immediately thinking about. And then there are 2 somewhat separate, very short-term memory stores. The visual spatial sketchpad holds images, and the phonological loop holds words, including words that we've just read. So if you close your eyes and then think about the layout of the image on the screen, you're using your visual spatial sketchpad to remember what you saw. If you close your eyes and then think about the names of the different parts of this model, you're using your phonological loop. Both the visual spatial sketchpad and the phonological loop have very limited capacity, and when you add new ideas, you lose older ones. Here's an example that demonstrates the important limiting nature of working memory. Just look at that top bit, 17 times 8. So I'm going to try to do that now in my head and explain the thinking as I go along. Right, so first of all, I don't know what 8 times 17 is. So to make that easier, I have an approach that I know will work. So I'm bringing that from my long-term memory. I know that if I split the 17 into a 10 and a 7, multiply each part by 8, and then add the 2 answers together, that that will work. So I'm remembering that because I've done it lots of times before. So I've got that idea in my working memory. So I now actually need to follow that process. So the first thing I do is 10 times 8, which is 80. So I need to hold 80 in my phonological loop. 10 times 8 is 80. I've done that bit. So now I need to do 7 times 8. And because I know my times tables, 7 8s are 56. So I need to put that into my phonological loop as well. So I've now got 80 and 56 in my phonological loop. And I know, because I haven't lost track of what I'm doing, that the next step is to add those two numbers together. So 80 add 56. Well, again, I'm using a bit of a strategy there. So I'm thinking, well, I need 20 onto the 80 to make 100. So instead of 80 plus 56, I'm actually doing 100 plus 36. My answer is 136. And with a bit of luck, I haven't actually checked. 17 times 8 is 136. But hopefully I've just illustrated a little bit how I've been holding ideas in my phonological loop in order to do that problem. Now, I can manage that, and I have just about enough capacity to explain what I'm doing as well as actually doing it. But I can only do that by drawing on ideas from long-term memory. If I wasn't very familiar with the approach that I used, or I didn't easily recall how to multiply 8 by 10, 8 and with a 0 on the end, or I didn't easily recall 7 8s are 56, then I probably couldn't have done that calculation in my head. If you gave me 173 times 8, I would have to hold more numbers in my phonological loop, and I might not have enough working memory capacity. How important is this limited working memory capacity? Well, if you try the little task that's on here, so take a problem you can manage in your head. Science might make sense, but you can do things like the arithmetic calculation that I've just done. And you break it down into individual items. So all those tiny little pieces like I just did for 17 times 8. If you do a good job of that, you'll see that even quite simple ideas, problems, have numerous steps to them and a number of things that you've got to hold in mind if you're going to do them successfully. And that will start to illustrate to you that the capacity to hold those things in working memory is really important and can be a real limiting factor in lots of the work that we do in the classroom. Right, okay, but how do we have evidence about how that translates to sort of successful learning in the classroom? Well, working memory capacity is quite an easy thing to measure. There are some good standard ways of doing that. And when you do that, it turns out that children do have different working memory capacities. So work on relating working memory capacity to outcomes on standardized tests in school has been done, particularly by Gathercole and her colleagues. And you can see some of that evidence here. So you might need to take a moment to work out what that graph is showing, but each of the bars is either the group of children within this sample who are achieving at a low level, an average level, or a high level in English. So that's the left-hand graph. And the 3 bars on the right-hand graph are children in groups at low levels of achievement, average levels of achievement, and high levels of achievement in maths. And then on the vertical axis, the y-axis, is the working memory capacity scores for those children, the average for that group. So what you can see there is that there's a very strong correlation between working memory capacity and standardized test scores. And standardized test scores are about the best evidence we have about how larger numbers of children are getting on at school. So the bad news is that working memory capacity does seem to be strongly correlated with learning at school. And at least as far as we know, there's no way to change working memory capacity. We've not found any way to do that at the moment. And it doesn't look as though that is possible. Working memory capacity does increase with age up to early adulthood, but I'm afraid some of us are just luckier than others in what we're born with. So children with greater working memory capacity will tend to find the sorts of problems they encounter in the classroom rather easier than those children with smaller working memory capacity. They will tend to pick up things more quickly and they'll tend to do better at school. However, it's not all in doom and gloom. There is some good news. You can see from the 17 times 8 example that solving a problem like that one isn't only dependent on working memory. If you didn't know to split the 17 into a 10 and a 7, or you had to work out 7 by 8 by, I don't know, counting up from 8s, because you know 5 8s are 40, and then it's 6 8s must be 40 plus 8, and 7 8s must be 48 plus another. Yeah, if you had to do that, then it would be a much harder calculation than it was for me. This is why learning your times tables has been an important part of primary school for most of the time, since children that age have been going to school rather than down mines or up chimneys. Long-term memory is effectively unlimited, so increasing the amount of useful stuff in long-term memory, getting it linked together and practicing retrieving it is one way to make working memory capacity less of a limitation. More about that in a minute. Another option is to write stuff down. That's how I cope with 173 times 8. However, the main thing I want to focus on at the moment is ways to avoid overloading children's working memory in your teaching. If you want to read more about strategies for supporting children who are struggling with having a relatively low working memory capacity, then Susan Gather-Cole, along with a couple of colleagues, has written a guide for teachers, which is really useful. You can probably find that by Googling. If not, you could drop me an email and I'll send you a link to it. Right, so the main thing I want to focus on at the moment, though, is ways to avoid overloading children's working memory in your teaching. So there is some evidence that you can have too much of a good thing here. If you make work in the classroom too easy, that will have a detrimental effect on learning, just as it will if you make things too demanding. However, as a trainee teacher, you're far more likely to overload working memory capacity than to make things too easy. So going to have a look at some ideas supported by research and classroom experience about managing load on working memory. In each case, I'm going to introduce some options, give you a moment to think which of those options reduces cognitive load, and then I'll try to explain. So here's two sort of general approaches in your teaching. Hopefully you've thought for a moment about which of those reduces cognitive load, and it's teaching in routines. So where stuff is kind of innovative and varied, there are lots of reasons why you might want to do that, but you should bear in mind that children are then having to think about what they're doing, you know, in terms of the nature of the task, rather than just thinking about the particular idea that you're trying to get them to learn. Whereas if your classroom runs much more on routines, then children don't really have to think about those. They're all in long-term memory. They're all easily recalled because they're used to doing them. And that means that there is less demand on working memory from that aspect of what you're doing, which means there's more working memory capacity available for thinking about the key ideas that you're trying to teach. So I'm not saying never introduce any innovation or variety in your teaching. I'm just saying that bear in mind when you do that, that adds to the cognitive load that the children are experiencing. So if in doubt, routines are good. So this is the difference between a problem, you know, question 4 on a worksheet, and looking at a worked example. Here's one that's already done. Can you have a look at this and work out what the different steps are? So have a think. And the evidence is that worked examples have a lower cognitive load than problems where the children are working towards an answer. So that means that when you're introducing new calculations or other sorts of kind of procedural knowledge, so in science, like Punnett squares for genetic inheritance, then it's often helpful to have worked examples for the children to look at before you move on to problems where they're solving from scratch. Hopefully that's self-explanatory from the little clarification underneath. And quite surprisingly, open problems seem to create a lower cognitive load. And the reason for this is that with a closed problem, you need to be thinking about the destination, where you're headed for in the work that you're doing. Whereas with an open problem, you can just start where it seems to make most sense and work away at it. That's not to say that all your problems in your teaching should be open problems, not at all. But you may not have come across open problems at all in teaching before, and it's a useful thing to think about. So in science, giving children a graph and saying, what are all the things that you can work out from this graph? And that's an example of an open problem, and that works really well. It won't be something you use all the time, but it's a useful tool in your toolkit. Okay, so this would be, the difference between a class practical and a teacher demonstration of some science experiment. And perhaps unsurprisingly, the demo is lower cognitive load for the children. They don't have to think about what they're doing because the teacher's doing it all. So they only have to think about what they're seeing. And as a teacher, you can obviously direct their attention to the things that are important, and that reduces the distractions that they might be thinking about if they're trying to make those decisions for themselves. By the way, the cognitive load on you when you're doing a demo and trying to explain and manage the class is quite high. So bear that in mind, but it will come with practice. That doesn't mean to say you shouldn't be doing class practicals. They're a really important part of science teaching, but don't underestimate the cognitive load that's involved. The children are spending a lot of time during the practical thinking about what they're doing and very little time about the underlying science. More of that when we do some training on practical work. Okay, so the diagram with the written explanation just includes more information. So the cognitive load involved in processing that is greater than just a diagram, but of course a diagram on its own might not be clear, might not have enough information. What about this? Okay, and this time you're making use of a feature of the model. Can you draw on your visual spatial sketchpad to remember what that diagram looked like, the model of working memory? So there are two parts to it. The visual spatial sketchpad processes the diagram because that's an image, and the phonological loop processes the or holds ideas about from the spoken explanation. So it seems as though we have these two channels. One is visual and one is to do with words. And by combining both of those channels, actually we slightly circumvent some of the limitations of working memory capacity. So a good way of presenting information is a diagram and a spoken explanation over the top. And that's easier for most children to access than a diagram and written explanation. And sorry, just to highlight one other point there. If you do a diagram with a written explanation and then you give a spoken explanation on top of that, then you've increased the cognitive load more than you need to, because the children are either trying to read and ignore what you're saying, or they're trying to listen and ignore the words that they can see associated with the diagram, and that adds to cognitive load. So the best way of presenting information where a diagram and an explanation is appropriate is to give the diagram and then a spoken explanation over the top of it. If you are putting written information on a diagram, then put it right on the diagram and keep the amount of text really brief, rather than having a diagram and then the text somewhere else near to it, sort of on the other side of the page, because the children are then having to think quite hard about which bit of text is associated with which bit of the diagram. You know, even if it's kind of A, B, C, D or whatever, it's much easier if the text is right next to the relevant bit of the diagram. Okay, here are 3 choices about engaging with written text, I suppose. Which of these is the least cognitive load? And the answer is the middle one. The reason for this is that if children are silently reading and their reading is not really good, you know, you will encounter lots of children whose reading isn't that fluent at secondary school, and then they're having to work quite hard at the process of decoding and kind of manipulating the information that's coming to them from the text. Whereas if you read the text to the children, then they don't have to do that reading process, so they can just focus on the information, on the words. It's really common to read text aloud with children following along, but then actually they're trying to do both things. They're trying to listen and they're trying to read. And really what they'll be doing is they'll either be listening and trying to ignore what they're following with their finger. You know, they're trying to hold their place, so that makes it more difficult for them. Or they're trying to read and ignore what you're saying, which again makes their life more difficult. So that's not necessarily to say that every bit of text you should introduce to children, you should just read it to them. You do need to think about what their reading fluency is like, but just bear in mind that sometimes the easiest way for children to access text, stuff that you might give them to read, is actually not to give it to them, it's to read it to them, and then maybe give it to them afterwards. Right. Earlier, I suggested long-term memory was effectively unlimited, but how do ideas get there in the first place, and how can we support that process in our teaching? Well, here is a quote: memory is the residue of thought. That has been quite a popular idea within teaching. What does it mean? Well, we remember what we think about. If you make children think hard about the thing that you want them to learn, then that's the best way of getting those ideas into long-term memory. But you have to be very careful to identify what it is that you want them to think about. So here's an example. Which way does the Queen's head face on a 10p coin? Actually, I'll make it easier. It's the same for all coins. Or British coins anyway. So which way does the Queen's head face on a coin? Don't look. Try and decide. Right, now, you've seen the image on a coin thousands and thousands of times. When you flip a coin, you specifically think about the image, don't you? Is it the Queen's head, or is it whatever the tail is on that coin? And yet, how sure are you, without cheating? I don't suppose you're very sure at all. You see, you've probably never had to think about which way the Queen is facing. It's not enough to see it thousands and thousands of times. It's not enough to focus on the image for hundreds of coin tosses. If you want to learn which way the Queen faces, you need to think about which way the Queen faces. It's that specific. So go and find a coin and check now. Pause the session if you need to. I made you think about which way the Queen faces. Hopefully you've made the effort to go and check. But have you learned it yet? By that, I mean, if I ask you again next week or next year, will you know? Probably not. Firstly, it's not linked to anything else much. This is why you should generally avoid introducing a new idea in science with a definition. Start with a concrete example instead and build up to a more abstract understanding. But secondly, you know right now, but you're going to forget, aren't you? I've done this every year for 5 years and I still have to check. Forgetting is, I'm afraid, a normal part of the learning process. So what can we do about this? Here is an experiment that has been done lots of times, including in realistic classroom settings. Suppose I asked you to learn the material in a chapter in a science textbook. You could read it once and then do several low stakes recall tests before a final assessment of what you'd learned. Or, second option here, you could study the chapter several times for the same total amount of time and then do the final assessment. Or you could not read the chapter at all and just do low stakes recall tests until it was time for the final assessment. Which is most effective? Well, depends a bit on the context, but it's always one of the testing options that works best. This is because low stakes recall tests provide retrieval practice, and the more we work at retrieving ideas from long-term memory, the easier that recall becomes. Over 100 years ago, Ebbinghaus did work on long-term memory that established this forgetting curve. You can see that each time ideas are recalled, they are forgotten more gradually. Eventually, they're not forgotten at all. Notice how the most effective approach is to leave the idea until it's fading and then try to recall it. This means the gaps between attempts to recall it should get longer and longer. With the coin example, maybe test yourself later today, then tomorrow, then at the end of the week, then in a fortnight's time, and so on. This principle is called distributed practice. You may well come across this principle in many schemes of work in your department. And again, it's a relatively new idea, I think, within teaching. So the sort of traditional way of approaching things is to teach a topic, do a topic test at the end of it, and then you don't go back to that topic for ages and ages and ages. So that's like the top version on this little diagram, where you have 3 lessons on something and then nothing. But with the information that we've got from the Ebbinghaus forgetting curve, that suggests that really what we should do is, after we finish the topic, we should keep coming back to it. And the gaps maybe should get longer and longer, but we shouldn't just leave it for ages and ages, because by the time we revisit it, lots of what children had already learned during the topic will have been forgotten. So revisiting ideas in our teaching is really important, and lots of departments will have that principle written into their schemes of work these days. Right, so far we've been looking at some ideas from cognitive psychology that can help with teaching and learning. However, until recently, the most prominent ideas from psychology within teaching have been from developmental psychology, not from cognitive psychology. So the 2 key figures are Piaget and Vygotsky. Let's start with Piaget. So Piaget introduced the idea that children go through 4 stages of development, 4 increasingly sophisticated ways of thinking. For example, if you fill different shaped containers to the same level, younger children tend to think they all contain the same amount. Older children tend to appreciate that if you pour fluid from a narrow container into a wide one, the volume will be conserved, but the level in the container will change. Another example is setting out the same number of sweets in lines of different lengths by changing the spacing. Younger children tend to judge by the length of the line, and older children consider the spacing and know that the length of the line is irrelevant if the number of sweets is conserved. Piaget thought these were different developmental stages, with children spending a long time in a stage and then fairly suddenly developing to the next stage. Piaget was wrong about that. More recent work shows that children think in different ways depending on context. In particular, they don't have to be ready for abstract concepts. You can teach them to work with abstract concepts. But Piaget was right that thinking about abstract concepts is generally more difficult than thinking about concrete things. You do need to be very careful not to make assumptions that because something abstract seems obvious to you, it will be obvious to the children you're teaching. Control of variable strategy is a good example. It seems pretty obvious, doesn't it? That if you want to find out how the mass, length, or angle of swing affect the period, that's the time for one swing, of a pendulum, then you need to start by changing one variable whilst keeping the others the same. Well, it's obvious to you because you've come across this idea hundreds of times, not just in the context of a pendulum, but in all sorts of other experimental work in science and other contexts. Don't assume it's obvious to children. You have to at least check, and you may well have to teach this multiple times before they've permanently learned it. So Piaget was wrong about cognitive stages, but you might notice children failing to understand things that seem obvious. It's not their developmental stage, they just haven't learned it yet. And that's your job as a teacher. But I think Piaget was right about a key element of the learning process. You can only learn something by linking it to other ideas that you already know. He called these linked ideas a schema. The process of learning is the process of adding to and improving the relevant schema. You have a sophisticated schema around the idea of an atom, for example. You've got ideas about what an atom is, its size, the subatomic particles within it, the arrangement of electrons, the way atoms are joined together in elements and compounds, and so on. You can easily hold a sophisticated set of ideas about atoms in mind, switch those ideas around, and maybe make use of them to process ideas about, I don't know, teaching key stage 3 chemistry. But there's no way you could think about how you might teach covalent bonding in a molecule if you only had a vague notion of what an atom is. For me, this is the key idea from Piaget. I've seen it echoed elsewhere, and it fits with my experience in the classroom. One of the most important things in teaching is to ascertain what children already know and start from there. However, there's also an unhelpful interpretation of Piaget's work on learning by building up schema. Piaget suggested that children have to construct knowledge for themselves. That's why this is called a constructivist theory. But this can be interpreted as meaning that children have to find things out for themselves. This interpretation suggests you can't directly teach control of variable strategy. You'd have to set up experiments in a way that led them to try out different approaches and then guide them to realize that the approach that works is the one where they hold all the other variables constant. I just think that's wrong. I'm not against illustrating the issue at all by using examples. That's great teaching, but don't shy away from telling them. And this is a major issue with constructivist psychology. It's tended to lead to constructivist teaching, and I think that has been unhelpful. Yes, the process of learning is an internal process of construction, but that doesn't mean we learn best by finding things out for ourselves. The other major constructivist theory came from Vygotsky. He developed some interesting ideas about how children's development is fundamentally tied to the social context in which they exist. He suggested that development occurs when a child is operating in the realm of what they cannot do by themselves, but can do with support. And he also suggested that development was intimately associated with speech. I'm not sure that adds much that's useful for teachers. It's sometimes been suggested that his work implies that ideas have to be developed by discussion between learners, for example, setting a problem and then putting children in groups to discuss alternative approaches. However, even if we were to accept his theory uncritically, I'm unconvinced that his theory leads to that conclusion. My experience in the classroom is that children can develop deeper understanding by talking about an idea, but if you put them to discuss in a group, that process is often unproductive. It's difficult to manage, and it's often the most confident children rather than the best ideas that drive the discussion. Right, moving on from a couple of ideas there from developmental psychology. Finally, we have an idea that's widespread but not supported by evidence. This is the idea that children learn best when ideas are presented to them in a way that matches their preferred learning style. There are lots of different versions of this, but the most common is that there are visual, oral, and kinesthetic learners. This has been tested numerous times, and there is no evidence that this is helpful. Ideas should be presented in the way that works best for the ideas. So you'd use a diagram for the parts of the digestive system. you'd say a new word like meiosis so children can hear it, and you would get children physically doing something if it's a motor skill like controlling a burette in a titration. It's a good idea to present information in a variety of ways or through a variety of tasks so children have opportunities to develop their understanding, but you should not be trying to provide visual, oral and kinesthetic options in your lessons. So that was a whistle-stop tour of some ideas that may, or in some cases may not, be useful in your teaching. And we will look at those ideas again. You'll come across them when you're working in the classroom and also in training that you do later in the year. If you want to take that a little bit further at the moment, then this presentation, these slides are on Blackboard, or you can just pause the video and work your way through them. But there are some true and false questions here about some of the things within this presentation, within this session, and you can have a look at these and have a think about which are true and which are false. Hopefully what that will be doing is making you think hard about some of the important ideas, and that will help them to stick in your long-term memory. So some questions here about working memory capacity. Some questions about long-term memory. And maybe a sneaky one about working memory there at the bottom. This is about things around retrieval practice. Again, there might be a question on a slightly different area there as well. And that's the end of this session.